Izzy, boom. Daniel, got it. Yes. Awesome, awesome. Okay, here we go. We got a verse of the day here, and then we'll pray and get straight onto this review. Only 12 problems, and we'll go backwards again. I made some problems for you guys, so we can go backwards through that. So the most recent to the least recent information there. Okay, the verse of the day is John 6:35. I am the bread of life. Jesus told them, no one who comes to me will ever be hungry, and no one who believes in me will ever be thirsty again. And so that's our desire. So everyone has this kind of God-shaped hole, and we try to fill it with stuff when we don't know God. But that's where everyone goes who is not a believer. So fill it with just stuff or people or whatever makes us happy, temporarily happy for the moment. But if we believe in Jesus Christ, we see that there's a new hope for life, and the fact that he died for us, and that God-shaped hole is now filled in us. So we have a genuine contentment and joy that comes from the Lord and the Lord only. So we don't have to rely on people or things to make us happy. And people and things will disappoint us because we are all broken and fallen, sinful people. There we go. That's the verse for the day. Let's go ahead and pray. Dear Lord, thank you for the conclusion to another wonderful week here in Mathland. We pray for a good review today, that all these lessons will be solidified and they'll come together for this test. We pray for clear minds as we go through this test, so at some point between after this class and the beginning of class on Tuesday. I pray that you'll be with us and guide us through all these questions that we'll see, and I pray that these examples will be good and we will gain a lot of understanding from them. I thank you for your Son, Jesus Christ, who died on the cross for our sins, and we pray these things in his name. Amen. Okay. Who's ready to review? All right, so if you have your review, I'm going to go through this guy. Oh, there we go. Let's see. I'll start at lesson 100 and go back from that. I don't know why my chat sounds aren't coming up. Hopefully you won't have to remember them. Yeah, well, I think the problem was I never got to those examples. There were two that we didn't get to, and those were the 2 or 3 that I took off because it was nuts. And if I don't find an example that are similar, you think going through all these lessons, you're like, okay, I know how to do this. I've done the homework, and then the test has some crazy weird type of situation, like, oh yeah, you did that in lesson 42. Like, not quite. I'm not sure how to do this. So I try to make up problems that are very similar to test questions so you aren't caught off guard. Like, ooh, what is this? Ugh, I don't know what's going on here. Okay, so we'll start with lesson 100. Okay, I made these up so they might not be super awesome, but I also found examples and page numbers and some of the homework problems that you've done. They're very similar to these. So I made up a lot of questions on the test. I think 5 questions I removed, and then I added 5 questions to this test. So I took off the weird ones that I saw immediately were super weird. So let's go with lesson 100. I'm going to go backwards through this review. Integrating variations of tangent and cotangent. Okay, so Gabriel, we just went over one of these from the homework. Which one was it? It was cotangent. Oh, it was 2 of them. Cotangent squared and tangent squared. Okay, so I'm just going to give you this guy, cotangent cubed x. And we've done this. We did it in our notes for lesson 100, and it's in the book for lesson 100. But we'll just go over this right now, just so you know how to split up a cubic of a cotangent or tangent. So let's split this up first. So we're going to take the integral of cotangent x and then cotangent squared x. Okay, if we can break it up, we can see parts and pieces that can be easily broken down. Okay, so here we go. Let's use the Pythagorean identity for this guy. Okay, so I'm going to keep this as cotangent x, and then use the Pythagorean identity, which is cosecant squared x minus 1. Okay, which equals cotangent squared. Okay, so then let's see. We'll keep it as cotangent x, and then remember what I just said before, Gabriel, with this guy. So we have secant, tangent, and then cosecant. negative. There's a negative in there. And cotangent. Okay, so if I have two of them here, my antiderivative is going to be cotangent, and that's what I want to get to with that. So let's see. Oh, let's see, what do I want to do now? Let's go ahead and distribute here. Negative cotangent. Yeah, it would be negative cotangent, but I'm kind of pausing right here because I think I want to separate this guy. Okay, so I'm going to, let me take a step back, and I'm going to distribute because I can also see that there's a u substitution we can use here. Knowing our derivatives of cotangent and secant, I can do a u substitution. So let's go ahead and distribute this. I've got cotangent x, cosecant squared x. Okay, so I know if my u is cotangent, my derivative is going to be cosecant. So I can squish that together and have a u substitution. That will be super easy and nice. And then minus, let's separate this integral to be cotangent x. Oops, sorry, dx. Okay, so I distributed and then I separated the integrals. Okay, so now in a different color, I'm going to take a u substitution here. So I'm going to say u is cotangent x. And then du, oh, how convenient, is actually a negative cosecant squared x dx. Well, I don't have the negative, so that's going to push out to the left. Put that on the du side, and then I have cosecant squared x dx. Okay, so I have that there. And that's my u. I'm just going to push out that negative to the left of the integral. Boom. And then I have, let's see, I have a u du. Oh, how nice. Lovely. And then over here, our cotangent. Know your cotangents. He's on a chart on, let's see, what's it? Lesson 100. And then also in the back of the book. So know your integral for cotangent. I'm just going to make a line here because it's in your notes. And it's one to memorize, especially for this test. Okay, so let's do all our u stuff here. So this would be negative 1/2 u squared, right? Okay, so let's put our u back in here. Okay, and then we'll have negative 1/2. Our u was cotangent, squared, because that was u squared, x. And this is minus the natural log of sine x, which is the integral of cotangent x, plus c. Ta-da! Okay, so we've done this one before. It's in your notes. It's in lesson 100. Cotangent cubed. Okay, that's a good one to know. Hint, hint. Okay, as long as you have work to show what you're doing, just stay on track. Separate them first and work them out that way with the secant, and then cosecant, negative cosecant. So those all work together. Okay? Yeah, good. Subtle, right? Okay, next was what, lesson 99? What do we have? Approximating radicals. Okay, so we had one like this. Hold on, I have to remove this. It was a weird one on the homework not too long ago. It was like yesterday's, I think, or the day before, where it had some other function with this. Now, the one on the test is just going to approximate the radicals. So it's not a crazy formula thing, so I'm going to make up one. The only difference here is I'm going to make it a fourth root. Look at this guy. Crazy. We haven't done fourth root yet, but it's the same process as doing a square root. So don't freak out. Don't freak out. So remember with the square root, we were trying to find a perfect square that's closest to this, either above it or below it. So here, let's see, what are we thinking here? The fourth root, the closest fourth root would be what? 16, right? Yeah, exactly. Okay. So if I'm thinking if I get, so maybe my f of x equals the 4th root of 16. So, oh, let's see, let's see. I want 16 to be my 4th root, so I'll say x equals 16. I kind of wrote that wrong. So maybe f of x is just a 4th root of x, right? Not this, sorry. I was thinking of everything together. Okay, so 16, that's my perfect 4th root, or quadratic, I don't know how. Anyway, that's the 4th root. So this is what I want to do. I want to take the derivative of this. So let's see. F of x equals the 4th root of x. Okay? Then take the derivative of this guy. And that's going to be, let's see, we're thinking x to the 1/4, right? Okay, so let's go ahead and change colors here. So that's going to be 1/4. And then x to the what? Negative 3/4. Like that. Ooh, and that's all negative, so it's in the denominator, right? And that's dx, because we took the derivative. Remember, dx is now going to be our difference between our perfect square root or 4th root, and the difference is going to be in between those two. So my dx is, since 16 is above, my dx is going to be, I'm going to put in -3, okay? That's the difference between my perfect one and then what I have here, okay? So let's see, I'm going to put that in here now. I've got 1/4 x to the 3/4. This is a -3/4. Yes, that's why it's in the denominator right here. It's in the denominator. Sorry, I wrote it kind of big. Just say 3. Because it's negative. We're going to have to subtract that later. You can put 3, but remember to subtract it later. Okay? And so I'm going to put a 3. I'm going to put a -3 to remind me this is to subtract it, because we're picking a number that's larger than it, so we have to subtract it to get to this approximation. Okay? So now let's work this out. If my x was 16, so f of 16. Okay, so let's put 16 in to where x is, and then we work this out. This is going to be -3 on top, and this 4th root of that is 2 cubed 8, 4, 32. Okay, so then all that is -3/32. The negative meaning to subtract it later on. Okay, so let's do our perfect one. That was the 4th root of 16. This is our perfect 4th root. So because we add 3 to, subtract it. Yes, because we chose a number that's larger than it, we're going to have to subtract that value from our perfect one. If we chose a number smaller than what we're given, smaller than 13, we'd have to add this value to it for the approximation. Okay. What is 19 instead of 13? We could just say 3, right? 19 instead of 13. Oh, yes, you're right, yes. Yeah, we would add that to it because we chose a number that was below it. Okay, so we're going to subtract it. I like to put a negative in here so it reminds me I'm subtracting this. So I'm going to take this whole thing and subtract it from my perfect 4th root here. So -3/32. Okay, so my perfect 4th root is going to be 2 minus 3/32. And you could work that out. Let's see, 3/32. I think I wrote that down here somewhere. It's like 0.09375. And then if you subtract it from 2, you get 1.90625. But you know what? You can just leave it like this. You can leave it like that. That's fine. That's okay. That's okay. Just leave it. Okay. So this is what you're going to do. If you chose a number that's larger, you'll have to subtract this approximation. Okay? If you're choosing a number that's smaller than it, then you're going to have to add to it. Okay? All right. That was from lesson 99. Lesson 98, Fundamental Theorem of Calculus. Okay, this was the one we kind of jumbled these two together. This was the, okay, kind of duh type stuff. Okay, so like this is lesson 98, right? 98. let f of x equal the integral of 1 to x. Remember, there was always an unknown x up to, let's say, make it weird, negative t squared, something like that. And then what does that original function look like, or that derivative of that function? I think the notation's like that. Okay, so this one, you just put an x. Put an x where you see a t. That's it. That's all you got to do. Because when we actually work this out, the derivative of the constant goes away. So, 1.9. Okay, yeah, well, whatever. I'm going to give you another hint on this one. If you leave it like this, it's okay. Wink, wink. Because it might be, I don't know, multiple choice. So it's okay. You don't have to sweat the decimals there. So this one's going to be 2e to the, oh, guess what? Negative x squared. Okay, so that's all you got to do. Boom. Plug it in. That's it. Don't think too much about this one. If you've got an x on the high part of that integral, leave it, leave it. Yeah, these are the best, right? Hopefully I don't have to throw out that one. Okay, and then was 97. 97. Lesson 97 is solids by cross-section. Okay, so I tried to make something up that would work here. Cross-sections, similar to what I saw on the test. Okay, so the cross-sections, I'm going to make it easy. It's a square. Although rectangles, I think, are the easiest. Square is a close second. Okay, so my boundaries for this, these are my, yeah, in the shell method. Like, oh, what do I do with that? There's a 2 pi somewhere. Ooh, what's going on? Okay, so I've got a base that is bounded by y equals 4. Oh, I lost Izzy. Where's Izzy? And then maybe x squared equals 2y. Now, there's a reason I'm writing it like this, and I'll show you in just a second. I know typically you wouldn't write, oh, y s squared, y, oh, that's ugly. Okay, so I've got to figure out what is going on here. So if I divided it by 2, it's still a quadratic, right? So I've got something, oh, and it's bounded by, let's see, the axes as well. Okay, so x and y axes. Okay, so I've got a parabola that opens up. And so if we move this around, it'd be y equals x squared, squared, over 2. Okay, hey, there's Izzy. Okay, still a parabola, still it's going to form a curvy kind of shape, and it's bounded by y equals 4. 1, 2, 3, 4. Okay, so this is the base of my 3-dimensional shape. Okay, what's kind of weird is that all the cross sections are squares. So if I were to try to draw this, okay, so here's my base. Okay, so I'm drawing it here. And then if they're all squares, if I drew a square right here, and then in all these other squares, it would kind of round down here and then kind of curve up there. I know it looks weird. So you'd have all these little squares here throughout. Okay, like that. Okay, so all those little squares, cross sections are squares. Yeah, I know. It could be worse, I guess. Okay, so cross sections are squares. Also, the cross sections are perpendicular to the y-axis. Important to know that it's perpendicular to the y-axis, which means if it's perpendicular to a particular axis, we have to write everything in our integral to reflect that axis. So our interval is going to be from 0 to 4, and our function has to be in terms of y. Oh, of y. That's why I wrote it like this. Yeah. Okay. So let's see. What do we have here? Let's put something together now. I've got volume is the integral on the interval of 0 to 4. And then let's see. I need my my area of my shape. whatever that cross section is. So a square, the area of that is what? If this is x and this is x, the area would be x squared, right? Side by side. Okay. Are these types of problems using any kinds of... Yeah, I think so. It's 3D modeling of some sort. Yeah, so I think... Sorry, you might see this again in an engineering field. Okay, so check this out. How convenient is this now? If my area is a side by a side... Okay. Let's see. Let's see, which one is this? It should give you the information. Every vertical cross section solid. Okay, it's going to say it's perpendicular. It's going to be perpendicular to whatever axis it is. Okay, so this is key. It's going to give you that information. So don't fret by trying to figure out how we do that. Okay, so the area of a square, that's side squared, right? Oh, look at that. In terms of y, I need side squared. Look at this. Oh, how nice am I? Hey, and it's sort of like this on the test too. So we just plug in this guy. Hello, 2y. It's already written in x squared format. That's all we needed. It's x squared. So it's 2y. 2y dy. How nice is this? Okay, so now we're evaluating it. So now this is going to be y squared, and then we're going to divide by 2. Oh, just y squared. Y squared from 0 to 4. So that's going to be what? 4 squared is 16. 16 minus 0. Boom, we're done. Units. Volume, we're units cubed, right? That's it. That's it. Don't overthink it. You don't even have to draw a picture if you don't want to. The graph helps because you have to figure out what axis it's perpendicular to. And, seeing the parameters there. Okay, but it's not too bad. It's very similar to this one. Hint, hint. Okay, so let's see. That's 97. Lesson 96. 96. Okay, that is evaluating absolute value integrals. Okay, again, this one's not too bad. We're going to evaluate this from -3 to 3 of this guy. Okay, and again, I checked out all these questions, and it's not crazy. So they're not going to give you something weird like 42x plus sine squared x absolute value. So this is very similar, very, very similar. Okay, so in our mind or on our paper, let's go ahead and envision what this looks like. Well, x plus 1, I know is the v, it's the absolute value. So we're going to shift it to the left, right? 1 unit. Okay, so it's going to be a v up there. It doesn't have to be super accurate. Okay, so let's think about this. We're taking the area under the curve, or in this way, it's kind of two rays coming together. So what if we continued this throughout, and maybe this was the function of x minus 1. I'm sorry, x plus 1. So maybe that's this part. If we just continued that segment here, boom. This would be the area here, and then that would be the area here. Okay, so maybe we can use that in setting up our integral. Okay, so we have a demarcation here of where we can establish a positive area and a negative area. Okay, because we have to have the sum of both because this is the absolute value. But knowing what we know about an absolute value of this particular function, we can evaluate it in 2 different steps as thinking of it as a linear function. Okay, does that make sense? I'm going to take it from -3, so that's -1 to 3. This is my stopping point. Let me put it in a different color. Stopping point, -3, and then 1, 2, 3. Let's say it's right here. Okay, so in this window, we need to find the area under the curve, but we need to use the negative area here if we use this as just a linear function. Okay, so we're going to go from -3 to -1 because that's where it crosses the x-axis there. Okay, and we're going to evaluate this as the linear function x plus 1, but we're going to put a negative there because the negative, you can put it out in front of the integral or put it right here. It might make more sense to you to see it on the outside because we have to evaluate the negative of that. So I'll put that on the outside. Okay, There we go. We'll put the negative of x plus 1 from -3 to -1 dx, and then we're going to add all this positive area here. So we're going to go from -1 to 3 of x plus 1 dx. Okay. I'm going to try to do this. Yeah. But this one's it's not weird. Like they had some crazy ones like the sine squared x, absolute value, and all that stuff. No, this is I found this one. It was a good one. Okay, so let's go ahead and maybe if we just distribute this negative, I put it out there thinking it would be better, but maybe we just distribute it here. So let's go like this, -3 to -1 of negative x minus 1, because we're just taking the antiderivative, and it's just a linear function, so it might be okay. So I'm going to rewrite it. Sorry. 1 dx. Okay, so now let's go ahead and... I keep pushing buttons. Stop. Go away. What is going on? What am I pushing? Oh gosh. Okay, well, it's going to be up there. Hopefully you can't see that. Okay. What is going on? Okay, sorry. This is, let's get the antiderivative here. I think you guys can evaluate from this point. I don't know how far I need to go here. Minus x. And this is going to be from -3, oops, to -1. What would happen if you didn't negate the first one? Then you would end up having, you would have this area minus this area. So it would be subtracted from your total amount. If you went from -3 to 3, remember the area under the curve, anything below the x-axis is going to be treated as a negative area. So it's going to be subtracted from any area above the x-axis. So you'd get a solution that would be less than your true area found in the absolute value of this. Okay. Let's see, plus this guy 1/2 x squared plus x. And that's going to go from -1 to 3. Okay, this is a 3. It looks like a B. Okay, so we're going to evaluate all that. I get 2 here. And then all that is the 8, and it's 10. I'm looking for area under the curve, so that's going to be, I guess, just 10. That's okay. It doesn't say area in units. That's 10. Okay. That's from lesson 96. Okay, lesson 94. 94, what do we have? Volumes of solids. Oh, yes, everyone's favorite here. So we have region R, a lot of areas and stuff like that. Okay, bounded by y equals x squared and the x-axis. And it's on 0, 2. And it's rotated around, about the, let's see, x equals 2. Okay, so it's its limiter right here. From 0 to 2, and it's going to be rotated about that. Okay, so good. We don't have to worry about some axis that's way over there, and we have to subtract that as well. So let me sketch this out. It's x squared, so, and the x-axis. Okay, so we're looking at things down here. 1, 2. So that's my boundary here for my interval. And I'm going to rotate about this axis. Oops, I'm making it hairy here. It's going to go about that axis there. So it looks like a y-axis. It's vertical. So I need to have things in terms, I need to have my function written in terms of y. So this is going to be the disk method, which I think is the first one we did. So we're going to find our disk is going to go around this axis here. But because it's a vertical axis, it acts like a y-axis. So we have to have things in terms of y. So in terms of y. Okay. So just like that one before with the cross section, whatever axis it's perpendicular to, this disk, it's got to be in that axis form. Okay. So in terms of y, right here, we have to figure out where it crosses. What's our peak right here, so we can make our interval in our y values. So let's see. 2, we know it stops at 2, so 2 squared is 4. Okay, I just plugged this value of 2 here into the x squared. All right, so we're going to set this up. Volume equals, put my pi on the outside. So if it was parallel to the y, would it still be disk? with this particular function, no, you'd probably do the shell method because it varies in the height. So yeah, because if you did this parallel to that, but what axis are we rotating around? We could do it like that. But if you're rotating around the x-axis, that would be okay. It would be perpendicular to the x-axis. So yeah. Again, this is very similar to a test question. Very similar. So don't overthink it. Like, this is it. Okay. What are we at? Pi. We're going from 0 to 4. Right? And then we have to get our radius of our disk. Okay? So think of it. Let's see. Where are we? Oh. Okay, so we're going to go 2 minus the square root. We have to have it in terms of y here, so we have to rewrite this. So y equals x squared, so x equals, I didn't put this in a convenient way, so we can write it like that. Ow, ow, ow. Okay, let's see, let me check something real quick, if I'm doing the right one. Let's see. Yeah, okay. So our right minus our left, so if we tilt our head, it's the y-axis, so the right side, that's 2. If we tilt our head, it's high minus low, or the right minus left. 2 minus the square root of y. And all of that is squared dy. Okay? Okay, because that's our radius. It's our radius squared. Remember, we're making a disk, so pi r squared is the area of that disk. Okay, so pi, and then this guy, let's go ahead and FOIL that out. So we've got 0 to 4. And we've got 4 minus 4 square root of y plus y, right? dy. Okay, check my math on that one. I think that's good. Okay, and then we can evaluate from there. I don't know if you want me to keep going with this one, evaluating this out, but you can plug in the numbers. It would be, let's see, let's go ahead and just get it to the antiderivative phase here. So that's going to be, can you keep going? Yeah, okay. So this would be 4y minus, this is y to the 1/2. Okay, so that's going to be add 2 over 2, so that's 3/2. So y to the 3/2. Oh, why did I put it over there? Y to the 3/2. And then we're going to multiply 4 by 2/3, so that's going to be 8/3. 8/3 y to the 3/2. Okay? Plus, this is just y squared. Oh, sorry, 1/2. 1/2 y squared. Boop. Okay, and then evaluate that from 0 to 4. Okay, plug these guys in. And, oops, I'm getting eaten. Okay, so do I need to go more with this? Plug it in. You got 16. It's going to be 4. 8 times 8 is 64. Minus 64, oops, over 3. That's going to be 16 divided by 2. That's plus 8. And then minus 0. Good, that's done. So add those guys all up and subtract that. And then put a pi with it. Boom, boom. And then it's going to be units, what are we talking? Volume? Units cubed. Okay, so keep going from there. I mean, it's just basic arithmetic from that point. Okay, is that good? Can we move on to the next one? Let me know if we need to work this out. Okay. All right, so keep going. Gabriel's typing something. Okay, I'm going to flip the page. Okay. Lesson 92. Okay, I'm trying to hustle through this. Okay, derivatives of inverse functions. Okay. This is, these are the weird ones. Okay. Let's do this. F of x equals 2x squared. That's a 2. 2x squared plus 5x. Let's say f of -1 is the inverse, which seems pretty obvious, of f. And I want to know what is the inverse for 7. If I put 7 in there. Okay, so let's see. If that's the inverse, let's see. Okay, so 7 has to equal. Did I write that right? Let's see. F of that. Let me check something real quick. Okay, the inverse of that one. Okay, so if this was the x value, I'm going to plug in 7 equals 2x squared plus 5. I'm going to use the original function to find that value. Okay, because remember the inverse, if this is the x value in the inverse, it's the y value in the original function. Okay, remember the inverses? Switching the x and the y. Don't switch anything. Just be aware that if this is the x in the inverse, it's going to be the y value. So I'm just going to set it as the y value to equal the original function. Does that make sense? Seems kind of weird right there, but that's how we have to remember it. Okay, so this one is one of those, well, if you try to figure this out, you'll get stuck. It'll be weird. But if you just look at the numbers, like step away from arithmetic, just look at the numbers, what could x possibly be? Well, you've got a 2 and a 5. That makes 7. So if x was 1, yeah, that's it. Okay. So one of those is going to be on the test. It's like, well, there's only one possible solution. Okay, and so using the same function, let's find the inverse derivative at 7. Okay, so we're going to set this up. This is our original function. We know that. So let me go off to the side. Let me do a different color so we can see it on the same page. Okay, so I'm going to start out with f equals my original function here, 5x. And then I'm going to take the derivative of this guy. So it's going to be 4x plus 5. And then I'm going to switch it, make it the inverse. So now I have x equals 4y plus 5. Okay, so derivative, then inverse. And then make the reciprocal of this 4y plus 5. Ta-da! Okay, so now we're going to plug this in, plug 7 in to that because it's the y. Okay, so then we're just going to multiply that out. So 4 times 7 plus 5. Okay, so that's 28. Okay, so that's 1 over what, 33? Here we go. That's it. That's it. Ta-da! Okay. That's all we got for that one on lesson 92. Shoot here. Okay. Okay, so why do we need to find x equals? It was a question they asked. They're not related in that way. It's like part A and part B. So do this and then there's that. It wasn't related to the other one. So it's like, can you do this? Can you do this? Not related. So don't try to make them relate. Okay, sorry. I'll label it A. I'll label this B. Two different questions. Okay. Let's see. What else do we have? Inverse functions 91. 91. Lesson 91. Okay. We're going to evaluate a limit as x approaches 0. And I've got 3x cosecant of 5x. Okay, so we're thinking we want to make this is like the L'Hopital's part 2, where things are multiplied or they're subtracted. So let's figure out how I can make it look like a quotient. How can I make things look like I've got a numerator and a denominator, so I can see if there's an indeterminate, and then I can use L'Hopital's for that. Okay, well, cosecant, that's 1 over sine. Maybe was the answer? Yes, I think so. 28 plus 5? Yeah, 1 over 33. Yeah. Okay. This is 1 over sine 5x. Okay, so now I've got a denominator thing going on here, and then my 3 can go on top. So I'm thinking of this as the limit as x approaches 0 of 3x over sine 5x. Okay? Yay. Now we've got a quotient set up. If we do direct substitution, what do we get? We get 0 over 0. Okay, well, that's not going to work. Okay, so get a nice little h equals. Okay, take the derivative of the numerator. That's going to be 3. Derivative of the denominator. Sine goes to cosine of 5x. We also have to take the derivative of the inner function there. So it's actually 5 cosine 5x. Okay, don't forget that inner part there. Okay, so when we plug in 0, let's do another direct substitution here. Let's see what we get. Let's see, we're going to have 3 over, let's see, cosine. 5 times 0 is 0. Cosine of 0 is 1. 1 times 5 is 5. Boom! We got an answer! Yeah! So use L'Hopital's, try to figure out how to make this a quotient in some way. So you might have a secant, you might have a cosecant, something like that. So recognize their identity with maybe sine or cosine there. Okay, that was lesson 91. Lesson 85. Okay, we've got using mean value theorem to find C. Okay, you've had a few of these on your homework. We can you can look over those. I've got one here. So use the mean value theorem by finding. Okay, and let's say I'll say find C in the interval 1, 5. And then I've got a function here, f prime of C equals, let's see, f of B, that's 5, minus f of A. This is the formula that remember the mean value theorem has this one, and then over B minus A. So this being A, this being B. Okay, so I have that, and then my function, let's see where I have a function, f of x equals 2x squared plus 3x minus 7. Okay, so here's my function. This is them pointing out what the mean value theorem is. And then we got to figure out what C is. Okay, so let's see. We have to do a couple things here. We've got to figure out what f prime of C is right here. Okay, so, well, if we do that, let's see. Hold on, let me figure out. I have notes on this, but I have to chase myself where I went. Okay, so let's see. Okay, if we plug in f of 5 into our function here, what do we get? So this is 25 times 2, that's 50, plus 15 minus 7. So I'm going to do, here's my f of C, and I'm plugging in f of 5. I'm going to do this right here. So f of 5 is going to be 58 minus, if I plug in my f of 1 into this function right here, I should get negative 2. Okay, and then below 5 minus 1, that's 4. Okay, so I'm just doing what they give me right here. They give me everything, all formulas right there. So plug in f of 5, plug in f of 1 into your function, and then divide it by the difference of a and b. Okay, so that's going to be, what, 60 over 4? Okay, which is 15. Okay, so I'm going to take this 15. That's f prime of C. So that's my solution to the derivative of this equation. Okay, so now I'm going to find the derivative here. F prime of x equals, what, 4x plus 3. Okay, this is the solution there if we're trying to find this mysterious C number, or in this case, I'm just going to leave it x. So I keep forgetting how we can just replace x with C. Yeah, the book changes out with C. I always leave it as x because x is going to be my unknown regardless of what letter it is. They always change it out. Oh, now it's C. So I'm just going to leave it as x. It could be, it's just an unknown. An unknown. Okay, does that make sense? The C just, okay, and why do we need to find the derivative of f of x? Okay, because this is the solution. 15 is the solution of that. F prime of C is this. So once we take the derivative, we can now solve for that unknown, whether it's C, whether it's x, whatever you want it to be, whatever letter. So then we subtract 3, we get 12 equals 4x, x equals 3. There is our C. We're looking for that specific number that would fulfill this whole thing on this interval. So it's from 1 to 5, and C is going to be that average height if we were to graph this. Okay. Or C is the point of that average height there. Okay, so that's it. So first, use the formula they have here, f of b minus f of a over the difference in that interval, and then set that equal to the derivative. Okay, and that was mean value theorem, lesson 66. Okay, almost done here. Okay, we're going to integrate this. We've got 5 over square root. We're going way back here, so it should get a little easier in the recall. Okay, this one, just use substitution. U is going to be, we have a quotient set up here, so I'm going to use my denominator or parts of my denominator. So 3 minus x du is just going to be a negative 1 dx. I can put 1 if I want to. Okay, I don't have a negative 1 in there, so I'm going to put a negative over here. Negative du equals dx. Okay, so then we're going to put this back in here. I'm going to put my 5 on the outside of 1 over the square root of, you know what, I'm just going to put it as u to the negative 1 half. U to the negative 1 half du. That's a half. All right, we know how to do this. We're going to add 2 over 2. Oh, sorry, the negative goes on the front. Oops, almost forgot that. Negative, don't forget that guy. He goes out there. Boop. Okay, so it's going to be negative 5, and the antiderivative, we're going to have, let's see, 2 over 2, so it's 1, oh, it's 1 half. So it's going to be 2 over 1, or just 2, to the u to the 1 half. All right, and then plug u back in there, so negative 10 square root of 3 minus x plus c. Don't forget your plus c. Here we go, plus c. Okay. Lesson 49. Ooh, getting close on time. Okay, so find the interval. Let's see, what is this? First derivative, second derivative, determine increasing, decreasing. Okay, so where is the graph? Oops, graph. What was it? Concave up. Concave up. Just do concave up. Yeah. So here's my function. Y equals 2/3 x squared. Oh, cubed. Sorry, cubed. Couldn't read my handwriting here. Cubed. Plus 3x squared minus 10x plus 2. So we do the derivative. We do the second derivative to find concavity. So now we have 2x squared plus 6x minus 10. Need to go again. Double prime for concavity. So this is going to be 4x plus 6. All right. We need to know where it's concave up, which means my y double prime has to be greater than 0. Has to be positive. That denotes concave up using the second derivative. Okay, so if this needs to be greater than 0, I'm going to set it up that way. So this guy, let's see, I'm going to put 4x plus 6 has to be greater than 0. Solve for x. So x is greater than negative 6 over 4. Or x is greater than negative 3 halves. So you can write it as an interval. Anything larger than negative 3 halves is going to be concave up. Ta-da! All right. That was a long time ago when we took a look at that one. Oh, and then we have another one. Lesson 46. And I'll be sending this video out if you need to look at other stuff. Okay, so this one, oh, related rates. Okay, so I'm going to read it instead of write it because I don't think we have enough time. It says the height of a circular cone is increasing in volume. So we've got a cone, and it's increasing, increasing in volume. Increasing in volume, Okay, at a rate of, of 5 centimeters per second. Okay, and the radius of the base is decreasing. So radius is decreasing at a rate of 2 centimeters. Centimeters per second. That's centimeters. Okay, find the rate. Find the rate at which the volume of the cone is changing. So find the rate, the difference in the volume. I'm going to put dV, just to abbreviate. Okay, which the volume of the cone is changing when the height is, something give you the height. Height is 10 centimeters, and my radius equals 2 centimeters. This is the last problem here. So I'm going to set this up. Oh, you might need to know the volume of a cone. That's 1/3 pi r squared h. Okay, so know that one. Hint, hint. Okay, plug everything in here. 1/3 pi. Okay, let's see, my r squared. Oh, let's find the derivative first. Sorry. Let's do the derivative of all this stuff. So I'm going to put my constants out here. Centimeters? Centimeters. Sorry. Centimeters. Centimeters. Okay. So I'm going to have, this is a quotient here. I mean, not quotient, a product rule here. So this is my first times the derivative of the second, which is the difference in the height, or the rate of the height, plus the height times the derivative of the first times that rate as well. Okay, so this is product rule. The first times the derivative of the second plus the second times the derivative of the first times that rate, the change of rate in the radius. Okay, so we've got 1/3 pi. Okay, plug in our radius now. So I have 2 squared. What's the difference in the height now? Well, it's going to increase 5 centimeters. So that's my 5 here. So this is the difference in the height here. Plus, what is the original height? It's 10 times 2 times my radius. 2 times the difference in the radius, which the increase